What time is it? Yeah. There is a delay. I'm warning you in this loop. Yeah, so it's very irritating. Okay, great. Okay. I think people will dribble in, but for the sake of time, I will start early because we have a cultural program, and this dancer and her team, they need some time with the stage to actually feel comfortable. So I will be brutal with timing for this session because we do want to vacate this place by 5:30 at the latest. So we have, you heard from Michael just before lunch, and we got a flavor of the quantum stuff going on at CERN, and Rohini and I worked hard so that Michael can visit Bangalore and IISc on Friday. And there's a lot of synergies between what he talked about and what expertise already exists in India, in particular IISc, TIFR, and other places. And now in this particular session, we worked very carefully and packaged them in 5 talks, and you will see that there's a lot of exciting opportunities. First speaker is Sujit Rajendran. Sujit actually, right now he's from Johns Hopkins, but I call him a California kid from Caltech, Stanford, Berkeley. He and I, he worked very closely with me to help us launch the quantum initiative in the US through DOE. So you will learn a lot about what we are doing there and what new ideas there could be. And this will be followed by 4 specially handpicked speakers this afternoon, including one from UK, that is Oliver, on atomic interferometry. And then there's Bivor Singh from Bangalore itself on cavity qubit, Vijay from TIFR, and Apurva from Bangalore also. So with that, go ahead, Sujit. Yeah. Okay, you talk.
Thank you very much. It's a lot of fun to be here. And today I'm going to talk about fundamental physics with quantum sensors. Now, given the overall goals of this meeting, I thought what I'll do is actually give you guys a bird's eye view of all the interesting science that could be done with quantum sensing for fundamental physics. So I'll talk about many experiments, but I won't have time, obviously, to go in detail in any of them. But I'll roughly tell you why these experiments should work, or what the excitement is anyway. And if you have questions about anything specific, please feel free to talk to me after the talk, and I'm happy to answer your questions. So here is the issue, right? We have a grand challenge in high-energy physics today, which is that the standard model has been experimentally established. This took about a century of work, beginning and largely done through colliders, beginning with the work of Lawrence and company in the 1930s, going all the way to CERN, with the discovery of the Higgs boson. And the standard model, every time we have asked a direct question about the standard model, it has said it's correct. There's no known experiment that actually directly violates the standard model. But we know there is new physics out there. This is not philosophy. There's more matter in the universe than antimatter. That's an observational fact. There's something called dark matter, also an observational fact. Both of these don't sit inside the standard model. So there is very clear reasons to think there is physics beyond standard model. It's just observationally true. Beyond that, we also have theoretical puzzles, such as the value of the dark energy, the cosmological constant, the hierarchy problem. Both of these are serious theoretical issues for which we don't really have any good answers. And more globally, we also know that if we take the laws of the universe and run the clock back in time, there comes a point where that doesn't work anymore. This is a so-called Big Bang. So there's certainly facts about the universe we don't obviously understand. So given that there is no doubt that there is new physics, the question becomes, where is this new physics? Why have we not found it? So as a theorist, I would say this is actually a question about the new physics. What is its mass and what is its strength? So the mass, we know what we mean by that. The strength, I basically ask, with what strength does this new physics interact with our standard model, protons, electrons, and neutrons, things of this kind. So in this two-dimensional plot, colliders have largely gone horizontally. They've gone of collisions to overcome your statistical issues. And a collider just comes with some luminosity, so it's not really that easy to go deep down in coupling if you want to find particles out there. But there is, I would say, considerable reasons to go and probe particles that are very, very weakly coupled. So examples of this include gravitational waves. We know they exist. We've discovered them, in fact. They are extremely weakly coupled particles. And then there are also things called dark matter and dark energy, and we call them dark precisely because their interaction strength, the standard model, can be extremely small. So given that there's a very strong physics case, in my opinion, to go and search these incredibly weakly coupled particles, the question really becomes, how are we technologically going to do this? And what is the challenge? The challenge is, if you're trying to find these incredibly weakly coupled particles, you're often thinking about detecting extremely small, weak effects. You may have to measure time to the accuracy of 10 to the minus 23 seconds, measure magnetic fields as small as 10 to the minus 20 Tesla. And the question is, how do you do that? Now, very naively, that might seem like a job for an engineering school, right? Go and build some extremely precise instrument. But actually speaking, when you're thinking about measuring something to this level of accuracy, this is really a question of physics at the end of the day. So let's ask this simple question. How can we measure time to an accuracy of 10 to the minus 23 seconds? Well, could we ask an engineer to go and build it, right? Now, an engineer, maybe someone in Switzerland, might work extremely hard to come up with a really, really nice clock. Great. So this guy worked very hard to come up with this very, very good clock. But no matter how hard this guy works, you know that because this is a macroscopic object, over time, because of things like friction, it will degrade. His ability to keep time will change. Not only that, let's say this guy makes his clock very, very carefully on day one, and on day two, he makes the next clock. How do we compare the clock that he makes on day one to the clock he makes on day two? Because you know that at some microscopic level, there will be some difference between one clock and the other. The gear on one clock will be somewhat different than the gear on the other clock. And so indeed, you really can't compare these two clocks. So with anything macroscopic, no matter how good an engineer you are, you're not going to get accuracy of this kind. And that's where you want to use quantum mechanics, a fundamental law of nature. And what you really want to make use of is this incredible fact. There are 10 to the 80 hydrogen atoms in the universe. And no matter where you get this hydrogen atom from, it's exactly identical to every other hydrogen atom. So if I gave you a hydrogen atom and someone else in the Andromeda galaxy gave you another hydrogen atom, you can't tell them apart. They're exactly identical. Quantum mechanics forces this on you. Not only are they exactly identical, it's also the case that hydrogen atoms don't degrade due to friction, right? I have a hydrogen atom today. It has some energy structures. Tomorrow, it'll have exactly the same energy structures, guaranteed to you by the laws of physics. So the whole idea of quantum sensing is basically, how can we leverage the properties of quantum mechanics fundamentally to create incredibly precise sensing platforms, right? You can see how the story works very sensibly. And so an example of this is the atomic clock, where you're basically using atomic energy levels as oscillators effectively to keep track of time. But you can similarly do this for magnetic fields, accelerometers, all kinds of things. So this is a field that is not new. I mean, people have been building these things over the last 2 decades or so, and there have been very, very impressive developments in this field. So today, one can actually measure magnetic fields smaller than about a femtotesla or so through squid and atomic magnetometers, accelerations as small as 10 to the minus 13 times the acceleration due to gravity, due to atom and optical interferometers, right? And this is a key point. Today, right, we have a lot of hype about quantum technology, blah, blah. Now, the stuff that I'm talking about is not some pie-in-the-sky stuff that doesn't exist. These machines exist. People can go and get them in the lab, right? So it's very interesting to ask how one could actually use existing technology and use that, leverage that to actually go after new physics. And what's even more exciting is that if you talk to people who actually work in these areas, these are not mature fields in any way. They're not saturated, right? There is every possibility that there's rapid technological advancements. And in fact, since I've been involved in this, these numbers have changed by 2 to 3 orders of magnitude every decade or something like that, right? So there's a lot of active areas going on pushing this technology forward. So it's interesting to ask, how can we actually use this technology to, say, go after gravitational waves, probe the dark sector, things of this kind? And much more recently, my interests have also drifted towards asking, well, given that we're actually using these very, very precise quantum sensors, leveraging quantum mechanics to make all these discoveries, could we use these to test quantum mechanics itself fundamentally? So that's kind of what I'm going to talk about very briefly today. I'll start by discussing how one can go after certain kinds of gravitational waves. Then we'll talk about how to detect certain kinds of dark matter. And then I'll briefly talk about trying to test certain modifications of quantum mechanics. And then I'll conclude. Gravitational waves. Well, the discovery of gravitational waves is one of the most historic things that humanity's ever done. 10,000 years from now, nobody will remember all the stupid politics that we lived through. People will remember the fact that we discovered gravitational waves. It's just simply true, right? Gravitational waves have given us a totally new way to look at the universe. It's equivalent to what Galileo did in the 16th century or whatever. And just like in electromagnetism, where pretty much in every frequency band that we have looked into it, we have found interesting new things. Whether this is radio waves or gamma rays, X-rays, wherever it is, the universe has always surprised us with what's actually out there. So it's very reasonable that gravitational waves will do something similar, that you might find new things out there in the universe that don't emit light, but are nevertheless copious emitters of gravitational waves because nothing can hide from gravity. So this may actually allow us to discover totally new things that nobody's ever thought about simply because gravity is universal. Not only could there be things that nobody's ever thought about, we actually know of things that exist and produce lots of gravitational waves, such as mergers of black holes, white dwarfs, and neutron stars. All of these are obviously of great excitement to astrophysicists generally. And very importantly, if you ever had ambition to go and discover the physics of the Big Bang, right? You have to look at the very, very early universe. And to look at the very, very early universe, you have to go behind the era of recombination from which we get photons. And the only known messenger that can go to the very beginning of time pretty much is gravitational waves. So there's obviously a very, very strong physics case to look at the gravitational wave spectrum wherever we can. The LIGO experiment detects gravitational waves from about 10 hertz to about 1 kilohertz. And there's now an interesting scientific question: how do we probe other frequency bands other than LIGO? So how do you detect a gravitational wave? This is the general cartoon big picture idea, okay? Different experiments are going to realize this big cartoon idea in different ways, but this is kind of what you need to do. A gravitational wave causes the distance between two objects to fluctuate, right? That's what it does. So how do you detect it? So let's say I have a very nice clock, A, and I have another clock, B. And let me separate them by some distance, L. Now, at clock A, what I'm going to do is every t seconds, t2, t3, t, I'm going to send light pulses from A to B, okay? And at B, I'm going to sit out there and record the time of arrival of these pulses. So if nothing is going on, the distance between A and B remains a constant. So even though I pulse the light t, 2t, and 3t, I'll receive the light at B at time t plus L, 2t plus L, 3t plus L. And so the time of arrival, since the distance hasn't changed, the separation is still t seconds, right? So like nothing has happened. But now say a gravitational wave goes by. A gravitational wave will cause the distance between these two objects to fluctuate. And when that happens, even though I'm sending the light from here at t, 2t, and 3t, the time of arrival will happen at t plus L plus epsilon, 2t plus L minus epsilon, so on and so forth. So if you simply sit there and measure the modulation of this arrival time, you can detect a gravitational wave. The reason why this is hard, of course, is because the effects of gravitational waves are extremely weak. So the time changes are extremely small. And so you need extremely precise technology to measure that very small length change. And just as importantly, you want to make sure that the distance between these two clocks does not change by any other noise source, right? So the gravitational wave creates an extremely tiny effect. If someone else came there and moved the watch back and forth, obviously you will see the noise and not the actual signal. So to detect gravitational waves, you need two things. You need extremely precise technology to measure this very, very small length change. And you also have to overcome all the systematics associated with making sure that the distance between these two objects only changes due to gravitational waves. So how does LIGO tackle this problem? What LIGO does is that they have an optical interferometer where they basically have two mirrors, all right, and they send light from a laser. It goes around two different arms. The light bounces between the mirrors and and comes back and re-interferes. So it's effectively measuring the distance between the two mirrors. So the optical interferometer is an incredibly precise way to measure the distance. But very importantly, the mirrors of LIGO are held from a ceiling. And when the world shakes, the ceiling will shake and the mirrors will also vibrate. So to prevent that from being a problem, LIGO has to create the world's best vibration isolation system. And they did that, which is why they detected gravitational waves. But there's so much seismic activity at frequencies below 10 hertz that despite LIGO's wonderful technology, you really can't see gravitational waves below 10 hertz terrestrially. So I would like to think about how one might try to overcome this problem in a different kind of terrestrial detector. So here is the idea. So let's create the world's best vibration isolation system. All right. Let's take the two mirrors of LIGO and let's drop them. Okay, so they're in free fall. As they're in free fall, let me try to measure the distance between them. Now, when a gravitational wave goes by, the distance between the mirror will still change, so you will be able to see the gravitational wave. Meanwhile, since the mirrors are in free fall, when the world shakes, there's no direct coupling between the shaking Earth and the mirror. So you have basically created the world's best vibration isolation system. Now, this is, of course, a brilliant idea, but this is a theorist's idea because nobody will let you do that, right? The mirrors of LIGO are 40 kilograms of sapphire, and so nobody's going to let you go and drop them. So the question becomes, instead of dropping the mirrors of LIGO, is it possible for us to drop something cheap, okay, yet something very precise? And the answer is you can. You can drop atoms, cold atoms, or atomic clocks, because that's what an atomic clock is. It's just clocks, atoms falling down. So let me rapidly tell you what the idea of this Majors experiment actually is. So this is the rough idea of what we want to do, right? Let's say you go to one of these mines in the world, and you go and find one of these kilometer-long vertical mine shafts that are there. What you're going to do is you're going to go to the top and the bottom of this mine shaft, and you will drop a bunch of ultra-cold atoms from the top and the bottom. So they're now in free fall. As they're in free fall, you use atom interferometry techniques to measure the distance between them, really the relative acceleration between these atoms and these atoms. So effectively, all you're really doing is think of these atoms as the mirrors of LIGO, and they're falling, and you're measuring the relative acceleration as they're in free fall. Okay? I don't have time to tell you how the atom interferometer actually works, but if you're interested, I'm happy to tell you the full details. So that's the main idea. And thanks to, in large part, to Swapan's effort, he managed to persuade Fermilab to actually want to look at some of these effects. So Fermilab is actually building a 100-meter scale apparatus to test and prove some of these concepts. And there are also many other groups around the world, Aeon in particular, that are also trying to do something similar in the UK. So let's switch gears and go from 1 to 10 hertz on the Earth. That's what we're aiming for with Majors, to something more ambitious for much lower frequencies. So there is a very nice idea on how to do gravitational waves at millihertz, and that is the LISA experiment, which I'm sure you've heard of. How does LISA work? The way LISA works is basically that they take 3 satellites, and inside each satellite, there's a little thing called a proof mass. And what LISA wants to do is measure the distance between this proof masses very, very accurately. So a gravitational wave goes by, the distance between the proof mass will fluctuate, and that is basically what they want to measure. Why is this challenging? Well, you're in space, so you might think naively there is no vibration problem, but that's not quite true, because you have a satellite around you. There is all kinds of stuff hitting the satellite, right? There's solar intensity fluctuations, charged particles doing things, all kinds of stuff, outgassing from the satellite, etc., which basically causes the satellites themselves to wiggle randomly. And when the satellite wiggles randomly, the random fluctuations of the satellite will gravitationally act on the proof mass and cause it to move as well. So if that movement is bigger than the gravitational waves, you can't detect gravity waves. So LISA basically had to fly and prove what is called drag-free motion, where basically these 3 proof masses that are inside these satellites can only move due to gravity and nothing else. All right? And that's called flying this drag-free. That's a technical term for it. It's extremely hard. And they had to fly a special mission called the LISA Pathfinder to prove that they could actually do it at the frequency of interest. So LISA Pathfinder worked very well, and they demonstrated that at millihertz, it would basically is at the performance level that LISA required. But an interesting question, what if you wanted to go to lower frequency? After all, there are gravitational waves everywhere. Now, the LISA Pathfinder showed that at LISA frequencies, they could do what they wanted. But if you ask how good are they at lower frequencies, they're not very good. Of course, they're not trying very hard to be very good. But at lower frequencies, the noise floor that they are in is considerably higher than what you would need to see gravitational waves. The question is, can we do something with atom interferometers and stuff like that in space now to go after much lower frequency gravitational waves, specifically at microhertz frequencies? So 2 things help you out as you go to lower frequencies. First of all, it turns out that the intrinsic strain of the gravitational waves you're trying to measure are about 10 to the minus 17 or 10 to the minus 18, which is about 6 orders of magnitude larger than the strains that you're looking at a LIGO. LIGO is like 10 to the minus 23. And that's fundamentally because at low frequencies, you're looking at mergers of extremely large black holes. These are just very, very violent events. So they give rise to much larger amplitudes and strain. Secondly, You can also separate, since you're in space now, separate two objects by something like 1 AU, as opposed to effectively the arm length of LIGO, which is about 1,000 kilometers. So essentially, if you want to detect gravitational waves of strain about 10 to the minus 17 or 10 to the minus 18, you need two objects in space, and you want the distance between them to be constant to about 0.1 microns. Okay, it's orders of magnitude larger than what LIGO is trying to get to. LIGO is 10 to the minus 18 meters. Right? This is 0.1 microns, considerably bigger. The challenge, though, is that you're at such low frequency that you still have to ensure that the two things don't move by more than 0.1 microns in, say, 10 to the 6 seconds. Right? How do you do that? So, of course, one could try to fly a LISA-like mission, but then you would require technology development to, make sure that you attain your performance goal at these low frequencies. So it's interesting to ask if there's something else one could do. Now I'm going to do the dumb thing, right? I have a force, random forces acting on an object, and I don't want the random force to cause a large position displacement. The dumbest way to do that is to put a very, very large mass, because A is F over m. But of course, I can't launch anything much bigger than a 1 ton. That's already very expensive. So what can I use? Well, maybe I can try to use natural objects. So the position of the sun, so the position of the planet Earth or Mars, things of this kind, right? So planets have extremely stable centers of mass. They don't move that easily. But even though a planet has very stable center of mass, its surface is what we have access to. And the surface of a planet is very noisy. The Earth has seismic activity. That's why we can't do most of these things on the Earth. Plus, there is all kinds of atmospheric effects, things of that kind, that also cause all kinds of waves. So what we really want is an object that is big enough that its center of mass is sufficiently stable. At the same time, it's small enough that it doesn't have internal dynamics, right? It's lost its heat of formation. There isn't weather, things of this kind. Luckily, we have such objects around us. They're called asteroids, 10-kilometer asteroids. Here's an idea. Suppose we look at two 10-kilometer asteroids, a few kilometer asteroid, and let me land two crafts on them, okay? And I'm going to put an atomic clock here, an atomic clock here, and I'm going to have a little radio station or a laser station that sends laser beams from one asteroid to the other. And I'm going to do exactly the same experiment. I'm going to use this clock, send light every t seconds, and I'm going to sit out there and receive light and see when it is arriving. If a gravitational wave comes by, the distance changes, and the time of arrival will modulate. I can do that. So is this possible? How much of this is science fiction? So first of all, can we land on asteroids? Bruce Willis showed this was possible in the 1990s. Okay, that just dates me. But in fact, for the last 20 years or so, humanity has been sending robotic craft to asteroids. Both NASA and the Japanese Space Agency have periodically gone to a variety of asteroids, landed on them, and done a bunch of stuff. Turns out, for technical reasons, that landing on an asteroid is actually considerably easier than going to another planet. Because let's say you want to go to Mars. You boost yourself to get off the Earth. And when you go to Mars, Mars has a pretty big self-gravity. So you need to go there and slow down. So anytime you watch one of these Mars landing videos, they have the last 10 minutes of terror or whatever it is, where all kinds of bad things could happen. But on an asteroid, since there is not much of a self-gravity, you can launch yourself so that when you get to the asteroid, the relative velocity between you and the asteroid becomes low enough that you just very, very gently land on it. Okay, so this has been done, demonstrated technology. Secondly, I require atomic clocks that are stable to 1 part in 10 to the 17 to 1 part to 10 to the 18 over this very long, this low frequency of about a microhertz. Those actually exist. If you go to Jun Yi at NIST, he's got these clocks, and they're not space qualified, but there's a lot of interest in creating a space qualified clock. And so, that part of the story also makes sense. So the next question, which is the actual scientific question, is how sure are we that the asteroid's surface and center of mass are stable enough? Okay. Now, it turns out that nobody's actually measured seismic activity in situ on an asteroid. They don't do it because they think it doesn't exist. So what we actually did was we went through the data for seismometers that have been placed both on the moon and on Mars and stuff like that. And from those actual measurements, it appears that there's a very reasonable reason to think that the surface of the asteroid would be stable to, let's say, 0.1 microns over 10 to the 6 seconds. Okay, so what we are trying to do now is try to get one of these asteroid guys to take a little seismometer with them the next time they go visit one of these asteroids, put it in there, and make a measurement. And if in fact they find that the seismic activity on an asteroid is less than 0.1 microns or so, there would be, I think, a very strong scientific case to just put an atomic clock and a laser station out there and then detect gravitational waves at a microhertz. Yes, yes. I'll be quick with the rest of the stuff. So I'll very rapidly tell you what we can do with dark matter. So here's the fact about dark matter. We know dark matter exists. Other than that, we know very little about it. We know that it can't have a mass lower than about 10 to the minus 22 eV or 10 to the minus 55 grams. That's for a bosonic particle. For a fermion, the mass can't be less than 10 to the minus 31 grams or 100 eV or so. And it can't be heavier than 10 to the 24 grams. That's all we know. 80 orders of magnitude in parameter space. So anything beyond this is a guess. And we have looked for WIMP dark matter for many, many years. It's a great thing to do, but we haven't found anything yet. So the question is, in my opinion, we should really go after this full parameter space. No theorist in the world can tell you exactly what it is. All right. So how do we systematically think about probing a large part of this parameter space in some reasonable way? So if you're thinking about detecting dark matter that is this light, okay, very low mass, it's very hard to find that through energy deposition because the amount of energy you deposit in every collision will be very, very small. What can you leverage? What you can leverage is that you know the total amount of energy density there is, and that is simply equal to the mass of the dark matter times the number density. So if the mass is small, the number density would be very, very high. So you're thinking about dark matter this light, you don't think about it as individual particles. You think about it as like a wave. It's a huge number of particles sitting in the same mode, and they're oscillating up and down at a frequency equal to the dark matter mass. So how do you detect this kind of wave? Okay, let's ignore the theory. Let's be practical experimentalists. To detect a wave, I have to ask, how does this wave influence particles that I control? Photons, electrons, protons, and neutrons. So how does a wave, a dark matter wave, affect these particles? Well, there's nothing specific about dark matter. I can just ask, how do waves affect these particles? And this is what waves can do. So say there's a dark matter wave, it's oscillating up and down at a frequency equal to its mass. It can drive a current in a circuit, push on electrons. It can cause some spins to rotate. It can exert forces on objects. And it can change the value of fundamental constants. That's it. Those are the experimental effects it's going to have. Now, if it drives a little current in a circuit, that will create a small magnetic field. If it causes a spin to rotate back and forth, that will also change the magnetization of a material. So you can stick a little magnetometer next to it, and that will try to see that effect. The dark matter exerts a force directly on objects that will cause an acceleration. If the dark matter changes the values of fundamental constants, even if you take two objects and the distance between them is not actually changing, when the fundamental constants change, the ruler that you're using to measure that distance, which is like the laser light frequency, will fluctuate. So it'll look like these objects are actually moving. So you can detect that with optical and atom interferometry, right? So this actually allows you, it turns out, to systematically probe a large part of this low mass dark matter parameter space that was previously not possible. So in the last 5 minutes, let me tell you about quantum mechanics and how one can try to modify it and test it. First of all, why? Think about it. Quantum mechanics was a theory that a bunch of people got together in a conference in the 1900s and said, these are the rules, right? Now, why should it be that people in a conference get to decide the rules forever? Why should it be the absolute truth? There's, of course, a sociological problem in physics, which is that when you tell people you're trying to modify quantum mechanics, they'll say the two things. Are you close to retirement? Are you crazy? As you can tell, I'm not close to retirement. Okay? So, but why does this sociology exist? And that's really because of the following thing. What aspects of quantum mechanics can you really change, right? All of quantum mechanics fundamentally rests on two postulates, probability and linearity. Probability is a fundamental part about nature. And many people have tried to modify quantum mechanics by trying to go after probability. But that's too hard. It's too much of a fact. And so it's not a big surprise to me that all of those efforts failed, right? And probability is what makes people most uncomfortable with quantum mechanics. So it's natural why they went after it. But I'm going to take a different point of view. I'm perfectly happy with the probabilistic world, all right? So given that probability is a fundamental part about the world, is it possible to change linear time evolution? Okay, why should the Schrodinger equation be linear? Surprisingly, not very many people have pursued this line of inquiry. Weinberg tried to do it, and let's see what issue he ran into. So let's do something very dumb. Take the Schrodinger equation, I d psi dt is h psi, and let me add a nonlinear term, right? Epsilon psi square, psi star square times psi. At the single particle level, there's no problem. You can go solve this and, perturbatively, you know how to do it. No big deal. What is the issue? The issue is that quantum mechanics has to describe more than one particle. And entanglement is a fundamental aspect of multi-particle quantum systems. So let's look at Weinberg's term and try the following. Let's say I give you an electron or something on the Earth, and it's entangled with another electron, let's say in Mars. All right. And I create this complicated entangled state, and I substitute this complicated entangled state in this equation, and I'm going to solve it to see how it's supposed to evolve. Now let's perform the following thought experiment. I will take the electron that I have on the Earth and apply some local operation on it. Okay, so I apply some unitary rotation on it. When I apply some unitary rotation on it, the coefficients sitting up here will all change. But when I have a psi square and a psi star square, if you go to the algebra, what you will find is that when I change these coefficients on the Earth, it will instantly change how the particle in Mars is responding, because I've changed the Hamiltonian in Mars the moment I did something on the Earth. And this was pointed out by Joe Polchinski. So of course, since Weinberg failed, people were like, of course, linearity in quantum mechanics must somehow come from causality. But the funny thing is that if you look at Polchinski's paper, after he pointed this out, the next part of Polchinski's paper is really about how there could be causal nonlinearities in quantum mechanics. And somehow nobody thought that through, including Joe. He didn't pursue it. So my own flirtation with this began with this following question. And this is just the main idea, okay? Let's just think about linear quantum mechanics. And let's think about how an electron that is coupled to electromagnetism is supposed to go from A to B. Well, it's supposed to follow the path integral. It takes all possible paths to go from A to B. And the key thing about linear quantum mechanics is that even though this electron is coupled to electromagnetism, these paths don't pull on each other. Okay? But if I put a second electron, and that electron also takes all of its paths to go from A to B, then even though the paths of each electron don't see themselves, this electron has no problem pulling on this guy. Right? That's just true. But if you think about it, isn't that bizarre? These paths could literally be on top of each other. So if you're bang in the middle of this path, how do you even know where this line came from? Why should causality all of a sudden show up and say, look, I can talk to my neighbor, but I can't talk to myself? Right? And if you think about this more, you realize that actually the way we put in causal interacting theories in quantum mechanics is not through single particle quantum mechanics, it's really through quantum field theory. Quantum field theory is a natural language to describe causal theories, interacting theories. So what we did in my paper with David Kaplan is we took a slightly different approach. Usually we think of quantum mechanics as an uber structure and quantum field theory as deriving it from it. What we said instead was like, no, I'm a quantum field theorist. Quantum field theory is fundamental. So let me try to put nonlinearities directly into quantum field theory. Turns out you can do that. Okay, you can go look at our paper and you can preserve all the things you want to preserve: unitarity, conservation of norm, maintain gauge invariance, all kinds of stuff. So as far as we can tell, this theory doesn't seem obviously wrong, right? Like there could be experimental reasons why it's not true, but that's exactly why we want to test it. So the one test that we have done is a very classic kind of test. You take an ion, you split the ion into two paths, okay? Half the ion, let's say, is here, the other half is there. And in linear quantum mechanics, these two arms do not talk to each other with the Coulomb interaction, but now in the nonlinear world, they will. Okay, there will basically be a phase shift in this experiment that depends upon the intensity of how much of the ion was in this side versus this ion. In the first round of the experiment that was done in the last year, we didn't find the result, okay, but we're going to try to do a much more sensitive experiment. So with that, let me conclude. And sorry for going a little bit over time. In the last century, we understood the standard model, and this was due to a hard work of an enormous community of people. And it really began because of a dramatic evolution in collider technology in the 20th century. This is a fact about the world. Why did this happen? The reason why this happened is because in the 20th century, humanity mastered electromagnetism, right? Maxwell wrote down the laws in 1867. Hertz discovered electromagnetic waves in 1887 or whatever. And then it took 30, 40 years for people like Lorentz to go and really understand how to come up with really good electromagnetic systems. And then we've done a lot of wonderful work in dramatically scaling up their power over the last 100 years. And we've learned a lot about the world in the last 100 years because of this. In my opinion, we are on a very similar level with quantum technology. We discovered quantum mechanics 100 years ago, but it's just now in the last few years that we are really at the anvil of quantum control, where we're actually able to control single quantum systems, manipulate them in ways that we really want to be able to do. Okay, so I would say we're kind of roughly at this Lorentz style level of being able to play with this technology and see what it does. So in my opinion, this is actually the right time in human history for us to go and make a concerted effort to try to find this weakly coupled physics, right? Because after all, if you think about the plot of new physics, you know, you got to ask yourself, the colliders did a lot of things and they went horizontally, right? Higher and higher energy. Now you got to ask yourself the following question. Are these discoveries simply because all the goodies, all the new physics is only along one direction? Or is it because that was the only direction that our technology was good enough to take us, right? I would bet that probably there's physics everywhere, and therefore we should try to look more broadly than we've been looking. Thank you.
Let's thank the speaker. Thank you, Sujit, for the exciting talk. I will entertain only 2 questions, okay, for this, okay? All right. Rajesh. I'm glad you came, and Ashok is here.
Hi, I enjoyed your talk. I had a couple of questions, but they're short. So when you said a dark matter wave can change the fundamental constants, did you mean it's like a dielectric kind of a change, or?
Oh, I'm just saying it's like an alpha modulus or an electron modulus, right? So you just take the electron mass, put a field in front of it, and so when the thing oscillates up and down, the mass will fluctuate.
Okay. And the second question is sort of a generic question about these asteroids.
Yeah.
Why didn't you consider the moon, which is also seismically not so active?
Right. Yeah, so the moon is actually a plausible place to go to. The thing is, we would require 2 base stations. So one could be the moon in principle, but you would still require another thing somewhere else.
Yeah.
And we just felt that in terms of things like landing, etc., asteroids may be easier, but you may be right that politically going to the moon may be a more profitable enterprise. So
or Mars has
Mars
2 moons,
as well.
has 2 moons.
Exactly,
Exactly. Because I was wondering, in the asteroids, isn't there a high probability of collision with other asteroids and so on?
So we're looking at essentially, I would say, inner solar system asteroids. So there are mostly collisions with small rocks. Now, specifically, the moons of Mars are not so good, because they're close enough to Mars. There's actually tidal strain that causes tidal quakes.
Thanks.
Okay, another question from somebody? One more question maximum. Okay, there, Vivek. Oh, sorry, right there. There's a question in the chat box.
But let me answer.
This is about your atom dropping down a shaft.
Yeah.
Now, wouldn't it be affected by micro changes in, say, let's say water seeps through? That would change. Because you're detecting.
You're absolutely right.
Some small seismic activity that causes a slight rearrangement in the rocks.
So the gravitational effects of that will be felt.
Yes.
And those are indeed very important. Yeah. And they're expected to be very important at frequencies below 1 hertz. So which is why I said 1 to 10 hertz is basically where I think the atom technology will really be useful terrestrially. Okay. You could probably go a little bit below 1 hertz, but that's very complicated question of the exact location, stuff like that. So we don't really exactly know that answer that one.
Thank you.
Okay, that's it. I think there's a chat question. How can we see this?
I can click
this question in the chat box.
In the presence of the solar wind, will the surface of the asteroid be stable enough? Yes, we checked that, because that'd be a good estimate, given that we know how much solar wind fluctuations there actually are.
Okay. All right. Okay. Thank you, Sujit. Thanks a lot to the speaker again. Right. So I'm going to call Vivor Singh. Vivor? Yeah, there you are. Vivor is going to talk about his work in Bangalore on cavity qubits, and basically he is a major component of the Indian quantum effort. So we asked him to speak about it, and Vijay will talk later on about what's going on in TIFR. Okay, before.
Later, right? Yeah, I gotta take care of this. Okay. Let me begin thanking Swapan and other organizers for inviting me to this meeting. And also actually for Michael, who made an interesting remark about why high energy physicists should be interested in low energy physics. So the talk that I'm going to give is actually towards the other extreme, towards the low energy physics. So my group work in the area of superconducting quantum devices. And the topic which was given for the presentation was rather generic. So I took the liberty of discussing two particular experiments from my lab. So broadly speaking, there's some delay, it seems. Broadly speaking, one can classify the superconducting quantum devices into several categories, and that's my characterization. So you have devices like superconducting qubits, which in the architecture of circuit QED or quantum optics are very useful for quantum computing. Then you have waveguide QED like structures. Again, the key ingredient for such devices are these different type of superconducting qubits. The other domain in which superconducting devices are making impact is in sensing and different kind of degrees of freedom, such as displacement force or microwave to optical photon transducers. It makes an impact there. We also heard earlier about single photon detectors, which can be made using these superconducting devices. Here are some examples. So this is one image of a superconducting qubit chip where multiple qubits are connected together to make something, a small scale quantum processor. Here I have taken one example of a sensing device, which is based on the idea of cavity electromechanics, where one can read out the displacement of this mechanically compliant aluminum drum and detect it to the short noise limit. The other domain is in memory. For example, superconducting devices can be coupled to different things, such as electron spins or electron spins in rare earths, or such as things like magnetic insulators. Okay, and these devices can be used to either create like a delay line for quantum state or to store the quantum information in these degrees of freedom. There are other peripheral devices, such as parametric amplifiers, microwave bolometers, and single photon sources. They can again be realized using these superconducting, they are again part of this superconducting quantum devices domain. My group at IISc works primarily in electromechanics and circuit QED. So we try to pose questions which comes from fundamental condensed matter physics, such as can we use techniques which exist in cavity electromechanics or circuit QED to answer questions which are there in condensed matter physics. So here is one such example where we use microwave cavity and a mechanical oscillator made of a superconductor to detect very minute charges. And charge sensitivity of such devices can be ordered like milli coulomb per nanometer. It's a line charge that we detect. The other domain is again applying these microwave techniques to larger structures, such as these mechanical resonators made from this nanowire, which can have frequency close to megahertz. And then you ask this question that using these techniques which exist in microwave domain, can one control the motional states of these mechanical oscillator down to their quantum regime? Okay. The other projects that we are doing are currently related to quantum computing, basically putting multiple qubits together and ask, can we control or apply small quantum algorithms on these processors? And as the number of qubits goes up, the requirement in terms of their control hardware again goes up. So in parallel, we are working on developing control electronics, which can handle these superconducting qubit devices. So these are a couple of projects that are going on in the lab. For the purpose of this talk, what I'll do is talk about this particular one, because it may be relevant to this community in high energy physics, and maybe briefly mention our efforts in developing this electronics for superconducting qubits. All right, so the idea that exists there to control the motional states of a mechanical oscillator comes from this cavity optomechanics. And like it was explained earlier, it's nothing but an interferometer, right? So the idea is that if you imagine a cavity where one of the mirror is subject to vibrate, it's connected, for example, to a spring, you shine light upon it, there are two things that are happening. If you detect the phase shift of the light that emits from here, you can detect the mirror position. And second is that as light kicks off from this mirror, it imparts it a momentum. Okay, it exerts a force on it. So if you can control the light, quantum state of the light which is entering, it's possible actually to take these mechanical resonators down to their quantum regime of motion. You can remove all the thermal noise and see the quantum effects. So this is the technique. The prototype that I showed you was in optical domain. Okay, where we had two mirrors and one mirror was subject to this spring. The interaction between them is this radiation pressure like, where intensity basically couples to the displacement of this mirror. And then one can define a figure of merit, which is the shift in the resonant frequency of this cavity due to the quantum 0-point motion of the mirror. So that's a natural figure of merit that arises in such system. Same thing one can in principle apply to microwave domain and make these cavities with LC circuits. Okay, so you take inductors and a capacitor. Yeah, I'll put it here so I can replace. All right, I'll try to speak in this meanwhile. So I was mentioning about these, microwave circuits, which one can make with inductors and capacitor. So if you imagine a capacitor with a mechanically compliant plate, then the resonant circuit, this resonant frequency of this circuit would effectively care about the separation between the capacitor plate. So the idea of parametric modulation that we had in optical domain is one can translate it to microwave domain by making these mechanically compliant capacitor. So here is an example of an LC circuit where this meander structure is the inductor made of aluminum, which superconducts below 1 Kelvin. And this disc-like structure here, that's a capacitor where the top plate is mechanically compliant, so it can go up and down. Typically, what happens that these microwave circuits are designed to work in the regime of like 4 to 10 gigahertz resonant frequency. And at sufficiently low temperature, due to high frequency and low temperature, they naturally initialize to their quantum ground state with very good fidelity. The mechanical frequencies, as the speed of sound is much lower than the speed of light, comes in the regime of 100 kilohertz to 100 megahertz. And with suitable engineering, one can get quality factors which are over than 1 million. Because the frequencies are lower, they still have some thermal motion, something like mean phonon occupancy of something like 10 to 10,000, depending on the frequency, of course. So the question that becomes is, what such devices are good for when it comes to displacement sensitivity. So here is the sort of a result from LIGO. If such devices are operating in optical domain, near 100 to 1000 hertz, one can achieve this strain noise, for example, which is ordered like below 10 to the power minus 23. Okay, it translates to a displacement sensitivity, which is like 10 to the power minus 20 meter per square root hertz. If you take this, similar experiment in microwave domain with these inductor and capacitor circuits, one can see similar figure like what LIGO has achieved, albeit the displacement sensitivity here is somewhat different. It's 10 to the power minus 14, minus 15 meter per square root hertz. But all the effects like imprecision noise going beyond the standard quantum limit and the effect of short noise of the microwave photons are visible in such devices as well, okay? So the fact that microwave photons are 6 orders of magnitude lower in energy as compared to optical photons, they are effectively reflected in the net displacement sensitivity when you measure them close to standard quantum limit, okay? So this is what can be achieved in terms of just the passive detection of the position of the mechanical oscillator. In terms of control, there are other experiments which has happened recently, such as demonstrating quantum entanglement between two massive oscillators. So you take two mechanical modes, cool them down to ground state, and then create sort of a quantum continuous variable quantum entanglement between them. So these two mechanical modes are essentially sharing a common microwave mode, and such entanglement allows you to push the boundary of quantum mechanics, as we have seen in the earlier talk. Okay, their results need to be interpreted more carefully to really detect if there are some new effects that are present. Other aspect of it is in long distance quantum communication. So again, this very nature, which is mechanical compliance, comes handy, and then one can design systems which works at the interface of microwave and optical photons. So these mechanical resonators can be part of a LC circuit, which is operating in microwave domain, and partly they can be embedded in an optical cavity. And one can ask the question that, can you make a transducer which will take a single microwave photon, convert it to single optical photon, and vice versa, without adding much of the noise and maintaining good efficiency and reciprocity. Okay, so this is another idea which is there in cavity optomechanics, where people are trying to build such transducer for quantum communication. All right, so having given an overview of what is going on with mechanical oscillators in quantum regime, I would like to tell you a little bit about what exact research we do in our group. So I'll take this example of the cavity optomechanical system that I introduced earlier to describe here. Okay, so the way I introduced this idea was that you take an inductor, and by making a mechanically compliant capacitor, one can realize this cavity optomechanical system. So if you think about it, at the heart of it is really the charge degree of freedom, which is causing this sort of a parametric coupling between these two. So one could ask that, can you have that freedom embedded in the inductor? Okay, and can one have some advantage if you include the mechanically displacement-dependent inductor in such circuit? Are there some advantages? The answer is yes. So the way a displacement-dependent inductor works is you basically make a squid loop, okay? And if one of the arm of the squid is suspended, then you would have a Josephson inductance, which would care about the net value of magnetic flux, which is passing through it, okay? So if this arm is going to move, it's going to change the magnetic flux through it, and essentially would change the inductance. So if we would have a displacement-dependent inductor, and if we shunt it with a capacitor, you have a resonant circuit, okay? The really sort of essential part of this scheme is that this Josephson inductance that the squid loop is providing is really a low loss, it's periodic, and it's nonlinear. So one can utilize all these three features to the advantage while making these optomechanical devices with it. So that's what we do. We make these squid inductors. So these are two Josephson junctions, and there is a nanowire embedded here. The dimensions of the nanowires are given here. And then, part of it, this circuitry is there is a big capacitor, which is not quite visible here, which basically comes in parallel with the inductors and form the resonant circuit. So such a device goes in a microwave cavity, which is shown here. This is made a waveguide cavity made in copper, because we also want to apply magnetic field to flux bias this squid loop. Okay, so if we apply a magnetic field which is perpendicular to the plane of the squid loop, it will become sensitive to the in-plane mode of vibrations. And if there is an in-plane magnetic field is applied, it will be sensitive to out-of-plane mode of vibrations. So these are the devices, and then in a nutshell, it would look something like this. This is a schematic. We can shine microwave to this 3D cavity, and then it will interact with the cavity as well as this LC oscillator that we have created using a squid. And then output can be measured in a dilution refrigerator. The net schematic of such a device is shown here. This is really for the experts. So what we have is we sort of attune these inductance and capacitance parameter in such a way that it's not a linear LC oscillator that we make, but we make an extremely nonlinear LC oscillator, so that upon quantization, it effectively looks like a two-level system, and we can call it a qubit. So what we have here is we have a flux tunable qubit, which is designed to work around 8 gigahertz. And then embedding it is a mechanical mode, which is at 6 gigahertz. The coupling that exists between these two is longitudinal type, meaning the displacement of the mechanical oscillator is causing qubit frequency to change. And then this qubit is being read out by coupling it to a linear cavity mode at 6 gigahertz. And the coupling there is again dipolar, like where field in the cavity couples to the dipole moment of the qubit. Okay, and then we have the microwave input-output lines. The reason I sort of emphasize on this particular slide was that if you think about it, now we have a system where you have essentially an internal degree of freedom, which is this qubit. It couples to a scalar mode, which is mechanical mode here. And if you make sort of analogies, this system is very similar to like a trapped ion system, okay, where we have a mechanical mode and a spin coupled together. But it's a solid state implementation of a trapped ion-like system. All right, so what is the current status of this experiment? Yeah, I think I should be able to do. So we start characterizing the electromechanical coupling. Like I defined, it's basically the shift in resonant frequency due to the 0-point motion of the mechanical resonator. And in the first generation of the experiment, we could achieve something like 4 kilohertz of a coupling by applying about 3.7 millitesla of magnetic field. So compared to those capacitive devices that I showed, it's certainly an order of magnitude improvement. And this coupling remains limited to the maximum magnetic field we could achieve in our lab, which is about 3.7 millitesla. This may seem very small, but one has to be careful while applying magnetic field to superconductors because they don't like each other. So this was limited to 4 kilohertz. What we learned from this experiment, that 4 kilohertz coupling was good enough to see something like an interference effect in the qubit spectrum. So while measuring the qubit spectrum, we see these small ripples. They are really coming from the coherence of the superconducting qubit, which is maintained over the mechanical oscillator. In technical details, this is known as Landau-Zener-Steckelberg interference. And it's a natural physics that would arise in a two-level system, which is simultaneously driven along longitudinal and transverse direction. This is something which we could very well understood from theory. And okay. So this is something which we could very well understood from theory and reproduce these results. Okay. Right. So this was the first generation of the experiment where we were using a rectangular waveguide cavity, which is really big, like 40 millimeter, and could achieve 4 kilohertz coupling. Recently, we modified it and went for coaxial cavities. They are really tight, like have 1 centimeter diameter, and we could apply larger magnetic field there without worrying too much about the superconductivity. And we could get something like 75 kilohertz coupling. As a consequence of it, if we try to work out, in terms of imprecision, noise, where we are operating, so I'll just remind you about a typical interferometer, how it's working. So one can reduce the imprecision noise by shining more light on this electromechanical cavity, okay? But as you increase the intensity of the light, the imprecision noise will continue to go down. But there will come the standard quantum limit where the back action from this light that you are sending would become important. And the point where the noise added by back action and the imprecision becomes equal to the 0-point motion, that's the standard quantum limit. Okay, so currently, the best measurements that we have done is we see an imprecision noise of something like 26 femtometer per square root hertz, and the 0-point motion of this nanowire is something similar, like 23 femtometer per square root hertz. The big advantage that we get because of this large coupling is we can achieve this level of sensitivity while maintaining a mean photon occupancy in the microwave mode, which is smaller than 1. So we are quite excited about these results, that while maintaining low photon occupancy, we can achieve such imprecision noise. And using these conditional cooling experiments or feedback cooling experiments, we would be able to control this mechanical oscillator better. Okay, so I'm not sure if I have time. So this is the current status of the previous experiment. I'll mention briefly about some of the other efforts that are going on in the lab. We are trying to develop classical control electronics for controlling these superconducting chips. And recently, what has happened is, pushed by this 5G technology, there are many evaluation kits available with high-frequency ADC and DACs on board. And they come with FPGAs so that, if one can design microwave pulses directly from these boards, one can implement things like feedback or quantum error correction directly on the board. So this is something that we are working on, and we have done some basic experiments using these, FPGA boards and demonstrate that one can, do traditional qubit measurements, superconducting qubit measurements, such as these time domain Rabi oscillations or measurement of T1 or T2 for these qubit devices. Next, what we are aiming is to include feedback in the loop and try to implement like active reset or protocols like that. In terms of, what is the advantage here is having multiple channels on the same board. It reduces the cost and also the complexity. It becomes much easier to do these measurements, having all these things on the board. Okay, so I think I'll stop here. I'll leave my summary here by showing these two images from these two experiments, and I'll be happy to take questions from here. And thanks a lot for listening to this talk.
Thank you, Vibhor. Thank you. Okay, let's a few questions here to anybody. Vibhor? No questions. Okay, thank you, Vibhor. This is all. Perfect talk. Thanks. All right, we move on to Vijay Raghavan. Vijay, is coming in. Is your talk loaded already? Yeah. Okay, he's going to talk about what he's doing at TIFR Mumbai.
When was this loaded? I sent it around 1 o'clock. Okay, maybe while the slides are being loaded, I'll just quickly introduce myself and sort of tell you a little bit of what I'm going to be talking about. I'm Vijay Raghavan. I'm an associate professor at the Tata Institute of Fundamental Research in Mumbai. And we started the first superconducting circuits lab in India back in 2012. It's coming up on 10 years now. And in the context of the session here, one of the topics we have been working on, both here and also before joining here during my PhD in postdoc, is actually working with the so-called parametric amplifier devices. These are highly sensitive devices which can amplify at the quantum limit. And as some of you might know, these kind of devices are now actually being used in dark matter searches experiments. So what I'm going to tell you today is a little bit about the work we are doing in our lab. And then towards the end, connect with some of the experiments that are being done in this area and then see how one can create a community here to look at these kind of experiments in the future. Okay, so I already mentioned this. Here is a bunch of topics on which we are working on. Apart from these parametric amplifiers, we do work on different kinds of novel qubits. The idea earlier on was to, reimagine what a qubit circuit could be. Vibhor set a nice stage in the previous talk of giving you different classes of qubit devices. And one of the qubits which he mentioned was just a simple nonlinear oscillator. So we started reimagining that how can you build more complex circuits? So one of them is this idea of multimodal circuits where you have more than one modes of oscillation. And each of those modes is nonlinear and hence can be used as an effective two-level system and a qubit. And they create a unique kind of a 3-qubit system for that. We're also working on solving the connectivity problems, like when you put down a network of qubits on a plane, you would like all of them to interact with each other on demand. So, but it's not so easy to do that. So how do you solve that? We have some ideas working on that. And I'm also involved in some more systems development kind of projects, sort of more engineering projects with funding from DST and also from DRDO. And the most ambitious one is to actually put together a full 7-qubit quantum computer. Of course, the world has gone quite far, and IBM recently announced 433. But this is still a big deal for us to put together actual system and see how to get these things to work properly. So here's just a sample of these images. So this is the 3-qubit circuit which we worked on. It's a novel qubit where the 3-qubit system, you can think of this as a coupled 3-qubit system. So it's sort of like an NMR molecule, except that we are doing experiments on one NMR molecule as opposed to an ensemble of NMR molecules, which is how experiments are done in NMR typically. A variation of this multimodal qubit is this device which we have called Quantramon, where we have actually used one of the modes, which is coupled as a measurement mode. Like you saw in the previous talk also, there's a measurement cavity for these qubits. So this kind of coupling allows some advantages in terms of how you efficiently you measure. So we're exploring some of those ideas over there. This is a fairly recent work which I mentioned about connectivity, where we are putting qubits around the circumference of a circular transmission line. So this is a transmission line resonator, sort of like with periodic boundary conditions. And what we are trying to do here is that we are trying to show that independent of where the qubits are located on the circumference, they can actually interact with each other. And that gives you a much more densely connected network, and that can have advantages as you scale up to larger processors. You want to create connections with as many qubits as possible so that you can implement algorithms in less steps as opposed to having to go through some intermediate qubits in a network. So, and finally, this was actually one of the earliest work we did back in 2015, where we introduced a very simple microwave engineering technique to improve the performance of these parametric amplifiers. So for most of the talk, I'm going to be explaining what these parametric amplifiers are, how they work, and then talk about what we did to improve them, their performance. So a very generic way of thinking about parametric amplification is to just consider some nonlinear medium, which is being driven by two signals. One we call the pump signal, and this is actually a very strong signal, and it sort of sets up the nonlinear medium in the right regime of operation. And then you send in another signal, which is a much weaker signal, and this is a signal you're actually trying to amplify. And ideally, what should happen is that due to this nonlinear medium, these two signals interact, and that interaction creates an amplified copy of the signal, but it also creates this extra copy, which is called the idler copy, and that is required by the physics of this system. And the pump sort of more or less comes out undisturbed, in the sense that even though the energy is being drawn from the pump for this amplification, and the energy has to come from somewhere, there is no other power source in this model. But the magnitude of this pump signal is so much higher than the signal that we assume it's essentially not changed. That's sort of an approximation one works with it. And depending on the nature of the nonlinearity, you can have two kinds of energy conserving processes when it comes to these frequencies, that one pump photon could break into one signal and one idler photon. So that could be one, this is called three-wave mixing, because there are three photons involved. Or you could have a situation where two pump photons break up into one signal and one idler photon. And this is called four-wave mixing. It really depends on what is the nonlinear system you have and how you set it up, to depending on which these two processes is being used. Okay. Now in the superconducting qubit domain, we have this fantastic element, this building block called the Josephson junction, which is basically a superconducting tunnel junction. So it's two layers of superconductor separated by a thin insulating barrier through which electrons, or in this case, Cooper pairs, can tunnel through. And this tunnel junction is represented by this symbol, which is a cross. And electrically, it behaves like an inductor. So the Josephson relations, which Brian Josephson wrote down to explain the electrical properties of this, tells you that the current through this device, which is the supercurrent, so current without any dissipation, is proportional to the sign of this quantity called delta. And delta can be thought of in multiple ways, but the second equation actually is a good definition of delta. It's sort of the integral of the voltage. So in some sense, it's like the flux in an inductor, with some constants in the front. And from these two equations, you can sort of compare this to how voltage and currents are related in inductor. You can get an effective expression for what the inductance of this device is. And you see that that depends on the amount of excitation present in the system. So it depends on delta, which means it depends on the current flowing through the system. So that's why it's a nonlinear inductor. And by putting two of these junctions in a loop like this, you can now make a flux tunable, nonlinear, non-dissipative inductor. So a magnetic flux now allows you to change the value of this inductance. The inductance is already nonlinear. And if you look at these equations, there is no dissipative term present here. Now, of course, this is an idealized representation. In principle, the dielectric could have dissipative processes going on, which can cause some dissipation, or your superconductor could still have some unpaired electrons, which can give rise to dissipative transport. But in the ideal case, this is a perfectly non-dissipative inductor. And the reason I'm emphasizing this is that typically when you think in optical systems, nonlinear systems come associated with a lot of dissipation. And dissipation is usually bad when you want to build an amplifier, which is basically an uncontrolled degree of freedom. So this is basically the element. And so how does parametric amplification work? One very simple model is actually that of a Fabry-Perot cavity, like shown here, where one mirror is being modulated at twice the natural frequency of resonance. Okay, this kind of modulation is called a parametric modulation. And if you do that, then one can show that any signal which is coming close to the resonant frequency of the cavity while this pump is on, it reflects back from this system with gain. So it absorbs energy from this pump tone. And so this will be a three-wave mixing process. And this can be implemented in the circuit form with the help of a squid, the one I showed you earlier, because it's a tunable inductor. So it creates sort of a tunable boundary condition for this Fabry-Perot cavity on chip. So this is nothing but a section of transmission line at microwave frequencies with two boundary conditions. One is a weak capacitor, so it's like a partially transmitting mirror, and another one is a variable inductor. So by passing an AC flux through this loop, I can create this modulation, which is equal to this picture, and then I can bounce off signals from this port here and get amplification. And people have used this kind of ideas to build these parametric amplifiers. The system I will tell you in a little bit more detail about is actually just a driven nonlinear oscillator. And in fact, this is basic Duffing oscillator physics. When I was first looking at this during my PhD days in the early 2000s, I found that this is discussed in Landau and Lifshitz mechanics books like in the 50s. So it's very old physics. It's just, it has become a lot more relevant in today's terms. So such a nonlinear oscillator, a Duffing-like oscillator, has a response. So this is oscillation amplitude versus frequency for different driving strengths. So for very low driving strength, it just looks like a simple harmonic oscillator, has a Lorentzian kind of response, has a peak at the resonant frequency and then decays on both sides. But as you increase the amplitude, especially at sufficiently large amplitude, you actually get these multi-valued solutions. So there are two stable states which are possible, one high one and one low one. And this just comes simply by looking at this driven nonlinear oscillator problem. But very close to the point where the system is about to get bistable, but not yet, is where the interesting stuff happens in the context of parametric amplification. The lower is just the same data, but plotted in terms of oscillation phase of this oscillator. Okay, so this is just simple classical driven nonlinear oscillator. So if we look at this now, treat this as a Duffing oscillator term. So this is now a Duffing oscillator driven by a harmonic drive. So we look for steady state solutions of this, just like we do for harmonic oscillator at the same frequency. And then you can say that, okay, I'm going to have some solution which is going to be at the same frequency at the drive with some amplitude and phase. I now say that I'm going to add a second drive. So this is now playing the role of the pump. The second drive is much, much weaker. And I'm going to basically say that I'm going to look for a perturbation kind of solution on top of this, where I say that the new solution is the old one with a small extra increment, with the condition that the drive for the second signal is much, much weaker than the first one, which consequently means that the value of y, this extra oscillations we are going to get, is going to be much smaller than the original steady state oscillation which the pump set up. So if you now do this and solve the equations, you get an effective equation for this y variable, which is the perturbing term. And this looks like, if you now look at it, has a second order term, a first order term, and a linear term here. There's something complicated in front, but otherwise it looks like a harmonic oscillator equation, which is driven by some signal, a weak signal over there. But it's this term here. If you look carefully, there is an overall coefficient, which is like the frequency square. But this is multiplied by a time varying term, which is proportional to twice the original pump frequency. So you see that now this driving term is close to double the natural frequency of this oscillator, but it's not exactly double. So that is a detail. So what I basically tried to show here is that a driven nonlinear oscillator effectively looks like a parametrically modulated harmonic oscillator. Okay, I've put harmonic here in quotes is because this equation is expanded for small values of y. Okay, so there are nonlinear terms, but we can ignore them for the lowest order solutions. Okay, and the pump is not exactly twice the effective resonant frequency because omega p is not equal to omega 0 effective. So it's not exactly. So we call it a detuned pump system. It has some practical consideration, doesn't change the basic physics. And the pumping strength, this K, is related to the original solution, steady state solution, which is X. Okay, so that's just a detail. So once you have that, then you have exactly the same system as before. So this system will also amplify signals which are sent to the cavity. Basically, it will amplify this signal omega s. So in practice, how does one use this? So this is actually the setup. You have your nonlinear oscillator here. You can have a flux input, but here the flux input's job is to only tune the resonant frequency to the desired value, because that sets the band of operation. Then you have this microwave device called a circulator, which is a 3-port device, and it only allows signals to propagate in the direction shown here. So an input signal from here, which is a pump, goes and biases up, and it reflects back and comes out at the output. You send your weak signal, that also goes, now combines with this pump signal, interacts in a nonlinear way, comes back out, gets amplified, and you get an amplified copy. And as I said, you also now get this idler copy, and this is a 4-photon process, so the idler is exactly at 2 omega pump minus omega signal, so it's equally spaced on the other side of the pump. And the point here, the important point here is that this picture actually tells you why this amplifier works at this very low noise limit, okay? Where is the noise coming from? So far, this is a completely noise-free system. I'm just talking about waves propagating in and out. In the ideal picture, if this is cooled down to low temperatures, you can say that the only fluctuations which are present are actually 0-point fluctuations corresponding to those frequency. So one simple model is that you assume, okay, the signal brings with it some noise, which is 0-point fluctuations. That gets amplified by the same amount, because this nonlinear system, which is just scattering these waves, cannot distinguish between signal or noise. It's just whatever comes in, it will just amplify it. But because there is going to be noise coming in from this other mirror frequency, which you cannot turn off in this case, that remixes into, because so initially signal was going from here to there and also cross like this, but now the noise from this side is going to mix into your signal band. And since these frequencies are all close to each other, their intensities of noise are also similar. So essentially what happens is that you get double the noise of what you started with. So if originally your signal to noise ratio had some value, now your signal to noise ratio is a factor of 2 smaller, with the difference that both signal and noise are about 100 times bigger. And that's really the purpose of an amplifier. So this is the quantum limit, that the best amplifiers can double the noise. And when you are at low enough temperatures, it will add only half a photon of noise corresponding to the 0-point fluctuations. And because these systems are very clean, they don't have any additional sources of dissipation, etc., you are able to build these devices and get them to operate very close to the system. If I don't do a good job of ensuring that unwanted noise is not entering the system, then I'm good. Otherwise, if I have some extra noise, if I don't do a good job of filtering everything, then that noise will also get amplified. But you can do this nicely in these systems. Okay, so this is has a flux tunable band. It's a lumped element design. This is sort of work I did during my postdoctoral days now, some time back. And it allows you to get a gain of more than 20 dB, has a bandwidth typically about 10 to 50 megahertz or so, and you can get quantum limited operation. Okay, and there are many, many applications of these kind of devices. One of the early experiments which I was involved in was actually to use this to detect the quantum state of a superconducting qubit in real time. What you're seeing here are real-time decay events of the qubit decaying from the excited state to the ground state. This was not possible before parametric amplifiers came on the scene, and now they are routinely part of all superconducting qubit experiments, and definitely all superconducting quantum computers, because you need to make these measurements fast and with high fidelity. You can also do things like quantum feedback, where you can stabilize the state from decaying because of this access to this very high quality measurement signal you have with them. And this also allows you to look at these systems in this so-called weak quantum measurement regime, and you can see how quantum trajectories evolve in the presence of measurement. So sort of demystifying the whole quantum collapse picture to some extent. And these nonlinear parametric systems are also a great source for microwave squeezed light, which has its own applications in many. And this is just a very small sample, and there are many, many things one can do with this. One of the other things is that this same device can actually be used as a very sensitive sensor of magnetic field. Why? Because this squid inductance depends on magnetic field. So any small changes in the magnetic field here will cause small changes in the resonant frequency, and that can be detected by shining a microwave light and looking at the phase shift of that microwave signal. But if you use the fact that this is a nonlinear oscillator and you bias it up, so you use a strong enough drive to bias it up to this nonlinear regime where this parametric amplification also kicks in, it gives you an inbuilt amplifier to the system. So not only you have a transducer which converts small changes in magnetic fields to changes in microwave signal phase, it also amplifies that signal and allows you to make a detector which is very, very sensitive to give you good flux sensitivity. And as Vibor was saying, this is only limited to how you couple to this resonant circuits parameters. You can have a mechanical system which could couple and modulate the frequency, the same thing would work. So it really opens up many, and you'll see some more in just a little bit. So at that time, we were also looking at, so this is again worked from during my postdoctoral days, but these are all systems which we can make in our lab now very easily. We were also looking at these different kinds of squids made using very narrow constrictions of superconducting material. So this is not a Josephson tunnel junction, but it's called a nano bridge junction or a micro bridge junction, but it has the same equations and works very similarly. And the advantage of having this very narrow, which is usually like a few tens of nanometer wide, is that you can now put magnetic molecules very close to them and study their properties. At least that was the hope behind developing these kind of experiments. The early generation of experiments were using low frequency DC techniques to detect the state of this qubit and how it gets affected. They were slow, they caused a lot of noise. So these new techniques of using high frequency microwave, and again, because this is a nonlinear system, you can bias it up and get parametric amplification as well. And that was shown in this paper many years back. Okay, so coming to now things which we have been doing in our lab itself. So one of the things I mentioned was actually we were able to improve the bandwidth of these oscillators with a very simple microwave engineering trick. Now, the reason the bandwidth is constrained for amplification is that this oscillator is a finite quality factor oscillator, which means that it only responds to signals very close to its resonant frequency. So that's one starting point itself gives you a constraint. But when you actually bias it up to this special point where you get gain, it actually slows down the dynamics and reduces the bandwidth even further. In fact, there's something called a gain bandwidth product, which you have to conserve. If you increase the gain, the bandwidth reduces. So we found a way to work around it by introducing just one simple extra reactive element. So this is again your nonlinear oscillator, the squid and the capacitor, and it's coupled to the environment, which is basically your transmission line. And we just introduced one very simple thing, and it sort of allowed us to cancel the reactance of this circuit and allowed signals outside of that usual band to get in. And with that, we were able to, and that's sort of the device. So all the extra part is in the circuit board here. This chip remained exactly the same. Now this idea has been adopted by many different groups around the world, and they're using various versions of this with integrating the transformers into the chip itself and many other variants of that. And we showed that from devices which usually give 10 to 50 megahertz of bandwidth, we were able to go all the way up to 600 megahertz of bandwidth without compromising on the noise. So the noise remained at quantum limited, and also sufficient power before it starts to saturate. This is one of the drawbacks of these systems, is that because I've ignored those higher nonlinear terms, they will actually start to saturate. The gain doesn't maintain itself if you send in a very strong signal to be amplified. But that's okay, because in most applications, the signals it's trying to amplify are very weak. Okay, so this was something we did a while back. And very recently, in fact, this paper just came out a few weeks back, we built this nonlinear oscillator using a different type of a Josephson junction. Now, this was in collaboration with Professor Mandar Deshmukh's group at TIFR, who's an expert at making these kind of graphene-based devices. So instead of, again, a superconducting insulator superconductor tunnel junction, this one uses a graphene as the tunneling barrier. And we use two different superconductors to connect them. But again, the physics is the same. It's a nonlinear inductor. Its nonlinearity is slightly different, but otherwise it's remained the same. So we are able to make this device. And one of the big questions with graphene-based tunnel junctions is that graphene in this context behaves like a normal metal. So it's an SNS junction. So there was always a question of, is it going to be dissipative? It is in some regimes, and it has less dissipation in other regimes. So in this experiment, we're able to show that the dissipation is small enough that we can actually use it to build, again, the same parametric amplifier, with this added advantage that now a DC gate voltage, as opposed to a magnetic flux, can tune the resonant frequency of this, because you can now dope the graphene with the help of an electric field. And this opens up a new way of controlling these devices. And that's really can be handy. So here, what we are showing is that the resonant frequency, which is this white line here, tunes with gate voltage over this range of about 10 to 15 volts. Okay, and then by choosing an appropriate point here, we were able to show that you can get parametric gain. This one did not have the bandwidth engineering, so it only had the standard 10 megahertz of bandwidth, but the noise was again very close to the quantum limit, which is set by this green dashed line. So the advantage of this kind of device is that it has first this gate voltage tunability. Because we use graphene and superconductors with higher values of TC, this can operate under a larger magnetic field. So Vibor had mentioned that superconductors don't like magnetic fields, and especially most of the devices we use are made out of aluminum, which cannot tolerate a lot of field. Here we should be able to put much more field that opens up possibilities of doing these experiments in different conditions. And finally, it opens up the possibility of building new types of quantum sensors and bolometers, because why? Now you have a graphene sheet there. So anything which affects the graphene, any kind of signal which can affect the graphene, it could be an incident photon, it could be something else, will now affect the property of the resonator and consequently can be detected. And you can take advantage of all the same techniques which I mentioned in the last few slides. Okay. So this is very recent work, and it was published in Nature Nano just a few weeks back. And now we are building up on doing follow-up experiments to look at other sensors. Okay, so coming towards the end of my talk, I'm flashing here some recent archive papers where some of these techniques have been used for dark matter search. So here's an example of an experiment where they did a dark matter Axion search using what is called the Josephson traveling wave parametric amplifier. Now, this device is something I have not discussed here at all. The difference is that instead of making a nonlinear resonator, which has a finite bandwidth, as I was just explaining to you how that constrains the operation frequencies and the band of signals it can amplify, you can actually make a nonlinear transmission line, which is sort of analog of a nonlinear fiber in optics. And then the same physics applies, but now you are less constrained by the natural bandwidth of this, even though it's not like an infinite band thing, because once you set up the transmission line with the pump tone, it introduces dispersion in the system, and that restricts the bandwidth. So people have been working and improving by doing all kinds of dispersion engineering. So going from 10 to 50 megahertz to about 600 megahertz using our simple technique to a nonlinear transmission line where you can get gigahertz of bandwidth. So this was the thing they've highlighted, that the ability of this Josephson traveling wave amplifier to deliver high gain over a wide 3 gigahertz bandwidth has engendered interest from those aiming to perform broadband Axion searches. Of course, this is just one part of the whole setup. There is a whole experiment there on what this traveling wave amplifier is actually amplifying. Similarly, there was another one recently about using near quantum noise limited detectors for dark matter search. So this one again uses what's called a phase insensitive JPA. JPA stands for Josephson parametric amplifier. And that allows them to improve both the signal to noise ratio and the speed with which data is acquired. And this has been done very recently. So personally, I have been following some of these very peripherally. I have not gotten into doing these kind of experiments yet, but the tools for developing these amplifiers we have in our capability in our lab and also in other groups around the country. So my interest is that I would like to develop new detectors. If a particular experiment says that we need this kind of a detector with these capabilities, that would be an area of research to work in. Also get involved in these kind of dark matter search experiments and other experiments which require sensitive detection. But currently what is missing and what we need, sort of especially in the Indian context, since this session is sort of about that, is that we also need other scientists who can design the experiments, right? As I said, the traveling wave amplifier is just one element of a whole experiment which already existed. So we need people who can design and work on those experiments. We also know to create links with the international experiments where we can contribute with our own expertise. So I'll stop there and take any questions. Thanks.
Okay, thank you, Vijay. So is Michael here sitting somewhere? Michael Doser? Hi, Michael. So you're getting an idea of what kind of capabilities there are, TIFR and here in Bangalore. So you'll hear some more after that break. So let's take a couple of questions before we go for a coffee break. Anybody have any questions? There, Michael. Yeah.
Yeah, one of the questions we have, of course, with the bigger experiments is scaling up from one to many, and many is many, many. How do you see that path?
You're talking about how to build many, many superconducting sensors?
Or how to combine many sensors in a single readout system? I mean, this is exactly the question.
So this, I mean, I have so far not worked on these aspects, but this is not very complicated or non-standard. In fact, this has been done in the context of MKIDs, these microwave kinetic inductance detectors. And there they need a multi-channel sensor anyway. And then each of those channels can have either their own amplifiers, or they can all be multiplexed if they are, frequency multiplexed, and then you send it to a broadband system. This is actually a very similar challenge to superconducting qubit readout in when you're building a quantum processor with 400 qubits. Are you going to have 400 amplifiers, or are you going to have 5 amplifiers which will each do 80 each or something like that? So I mean, these are, I think, engineering challenges, and when posed can be solved. I mean, they're not easy, but I think there's nothing fundamentally preventing one from doing. The fundamental issue will come if the original experiment, which is actually the front end, the receiver which is detecting either dark matter or gravitational waves, if the operating conditions of that are incompatible with the operating conditions of a superconducting sensor. So say very high magnetic field or very high temperatures, then there could be an issue. But again, these experiments I mentioned have shown that at least in some cases it is possible to make them compatible. And one can look at least going from, the experiments I showed are all dilution refrigerator experiments, 10 millikelvin. In principle, one could push it to 4 Kelvin liquid helium kind of operation. The noise might be a little bit worse, but there are probably tricks one can play there as well. And there's scope for innovation over there. Currently, these amplifiers, basically, whatever temperature they're operating at, that's what set the noise. Yeah.
But you have put the finger on the right. I mean, Apurva has challenged me with the same question. How do you add so many sensors into a coherent array so they can act together as a large sensor? It is going to be a big challenge for us. It is, and we'll talk about that maybe on Friday. So,
I mean, I would add a comment that I can imagine that it's easier to put thousands of amplifiers of this type than thousands of qubits.
We'll put you to test for that. Okay, another question before we move. Okay, yeah, well, go ahead.
Hi. Somewhere in the middle of your talk, you put an impedance element in a circuit and you increase the bandwidth.
Yeah.
Can you just? I mean, I didn't quite catch. Yeah, there. Yeah. So, how did this actually work?
So basically, the element we use here is a simple linear LC circuit, which is practically implemented as a lambda by 2 transformer, but that's just a technical detail. But a linear LC circuit, which is exactly resonant with this pump frequency, sort of cancels the capacitive roll-off of this original oscillator. Okay. This was actually an accidental discovery we did when we were playing around with the simulating these circuits. So then, we worked with some theorists to figure out, okay, one can explain this from analytics as well.
That's neat.
That part has actually been known in other fields in a different context as well, where one tries to pump in energy into resonance systems, but you want to So you use the resonant system to enhance the quality factor so that you can get a current amplification, but then you lose bandwidth. So you can introduce more modes. So it's some kind of band pass filter, if you like, where so sort of going from some very narrow band thing, you make it flat and make the roll off a little bit different. So it's a very simple microwave engineering trick applied to this specific case.
Okay, I think we're going to break for coffee now.
Yeah.
And come back 20 minutes past the hour, please. Sharp 20 minutes past the hour. Thank you.
Thank you.